A fifth of the entire sky is hidden from our view. This is the Zone of Galactic Obscuration, a vast region behind the Milky Way's dust and stars that remains an enduring blind spot for astronomers. By the end, you will see how hidden galaxy clusters and cosmic filaments, once revealed, could answer some of astronomy's biggest questions. How many galaxies lie completely unseen? And what massive structures are pulling our local group through space? What do you think might be hiding in the most obscured part of the sky? Deep behind the Milky Way's veil, a gravitational giant tugs at our galaxy. Astronomers call it the Great Attractor. This is not a single object, but a vast concentration of mass, so powerful that it pulls entire clusters of galaxies toward itself. Our own local group, which includes the Milky Way and Andromeda, is moving through space at roughly 600 kilometers every second. Much of that motion is directed toward a point in the sky near the constellations Triangulum and Norma, a region that overlaps heavily with the Zone of Obscuration. The Great Attractor's presence was first inferred not by seeing it, but by measuring the peculiar velocities of galaxies, which are deviations from the universal expansion. By mapping these movements, scientists realized that something massive was drawing galaxies in from all directions. In the 1990s, researchers using X-ray telescopes and radio observations managed to peer partly through the dust and found a dense cluster of galaxies at the heart of this flow, the Norma Cluster. This cluster is only one piece of the puzzle. The Great Attractor itself appears to be a much larger structure, possibly a supercluster, but its full shape and composition remain stubbornly hidden. The dust and stars of the Milky Way block our view of perhaps tens of thousands of galaxies and the gravitational well they form together. So the question becomes, what total mass lies concealed in that obscured patch of sky? And if so much is hidden, what else might be influencing the movement of galaxies across the local universe? The Great Attractor is a reminder that our cosmic neighborhood is shaped by forces we still cannot see directly. Every galaxy in the universe is built from the same fundamental ingredients, yet astronomers keep losing track of more than half of all ordinary matter. This is the missing baryon problem, and the Zone of Galactic Obscuration may be where many of those lost atoms are hiding. Baryons are simply the protons and neutrons that make up stars, planets, gas, and everything we can touch. When scientists calculate how many baryons should exist based on the early universe, they find that what we can see in galaxies and gas clouds today accounts for only about half of that predicted total. The rest must be somewhere, but it is extremely difficult to detect. The leading theory points to a diffuse, ultra-hot gas spread across the vast spaces between galaxies, known as the warm-hot intergalactic medium, or WIM. This gas reaches temperatures of 1,000,000 degrees or more, so it glows mainly in X-rays and certain ultraviolet wavelengths. The problem is that WIM is so thin that its signal is incredibly faint, easily drowned out by background noise. And where does the densest concentration of this elusive gas likely reside? Right behind the Milky Way's dusty disk, in the Zone of Obscuration. Astronomers have tried to catch glimpses of WIM by looking for absorption lines in the light of distant quasars. When a quasar beam passes through a patch of hot gas, specific wavelengths of light are absorbed, leaving a telltale fingerprint. But the zone blocks most of those background quasars from view, and the thick interstellar medium of our own galaxy scatters and dims whatever light does make it through. So even when a hint of WIM appears, separating its signature from the foreground fog is a nightmare of data analysis. Recent surveys using space-based X-ray telescopes have found tentative evidence of warm hot filaments along the edge of the zone, but the results remain uncertain. Every new observation chases a ghost that is just beyond our reach. Solving the missing baryon mystery would not just plug a hole in our models. It would confirm that the universe works the way we think it does, from the Big Bang down to the formation of every galaxy. And the final piece of that puzzle is almost certainly sitting there, hidden in plain sight behind the very stars we call home. Right at the center of that gravitational mystery sits the Norma Cluster, and it is almost invisible to our telescopes. This cluster is the closest massive gathering of galaxies to the Milky Way, yet it remains one of the least understood. Located in the constellation Norma, it lies directly behind the thickest part of the galactic disk, where dust and stars block nearly all visible light. Astronomers have had to rely on radio and infrared surveys to peel back that curtain, and what they have found is a surprisingly rich and dense system. The Norma Cluster contains hundreds of galaxies, possibly more than 1,000, packed into a volume only a few tens of millions of light-years across. Its total mass is estimated at something like a quadrillion times the mass of our Sun, making it a true heavyweight. But those numbers come with large error bars because the dust makes it so hard to measure faint members of the cluster. Many smaller galaxies, dim and easily lost in the foreground haze, could be hiding just beyond detection. The real puzzle is how far the cluster extends. Its core is well defined, but the outer boundaries are fuzzy. Gravitational studies suggest that the Norma Cluster may not be an isolated object. Instead, it might be the dense central node of a much larger structure, a filament or wall of galaxies that stretches deeper into the zone of obscuration. Some researchers suspect that the Great Attractor is not just the Norma Cluster itself, but a vast supercluster complex that includes the cluster and many other groups spread across the hidden region. If that is true, then the Norma Cluster is only the tip of an iceberg whose full size we have barely begun to chart. Infrared surveys from the 2-micron All-Sky survey and the Deeper WISE mission have revealed more galaxies in that direction, but each new detection raises fresh questions. How many more lie unseen? Does the cluster continue into areas where even infrared light is absorbed by the densest dust clouds? Determining its true extent is not just a matter of counting galaxies. It is about understanding the gravitational architecture that shapes the motion of our entire local universe. Every galaxy we discover hiding behind the veil brings us closer to seeing the full picture of what is pulling us through space. A structure as vast as the Sloan Great Wall could be concealed behind our galaxy. The Sloan Great Wall is one of the largest known cosmic formations, a gigantic filament of thousands of galaxies stretching over 1.4 billion light-years across. It was discovered in the early 2000s by the Sloan Digital Sky Survey, which mapped the distribution of galaxies in the nearby universe. But that survey, like most optical ones, had to avoid the zone of obscuration, leaving a great empty wedge in its map. Now, redshift surveys that push into the hidden region, such as the 2-micron All-Sky survey and the 6-degree field galaxy survey, have started to reveal hints of something just as massive on the other side of the Milky Way. These surveys measure how fast galaxies are moving away from us, using the stretching of their light, a method called redshift. By plotting those velocities in 3 dimensions, astronomers can see where galaxies cluster together. And in the direction behind the Norma Cluster, the data shows an unusually high number of galaxies spread across a huge volume. The pattern looks like a wall, a dense sheet of galaxies that runs roughly perpendicular to the Milky Way disk. If this structure is real, It could be comparable to the Sloan Great Wall in size and mass. The problem is that the measurements are incomplete. Many galaxies in that direction are so heavily obscured that only a fraction of their light reaches our telescopes, making redshift estimates uncertain. Still, the evidence is strong enough that some researchers have already proposed a name for it: the Great Wall behind the Milky Way. Confirming its existence would do more than add another supercluster to the catalog. It would complete a missing piece of the cosmic web, the skeleton of filaments and walls that connects all galaxies across the universe. Right now, our maps of that web have a huge hole right where the Milky Way sits. Finding a wall there would show that the web is even more interconnected and extensive than we currently understand. It would also help explain the motion of galaxies in our local neighborhood, because such a massive structure would exert a gravitational pull that ripples across hundreds of millions of light years. Every new redshift survey that peers deeper into the zone brings us closer to deciding whether this wall is real or just a trick of the dust. And if it is real, then the zone of obscuration is not just a blank spot on our maps. It is a hidden continent, a vast hidden realm of the universe waiting to be charted. At the heart of our galaxy lies a hidden engine that reshapes everything we try to observe beyond it. The supermassive black hole called Sagittarius, a star, sits at the very center of the Milky Way, a region packed with stars, gas, and magnetic fields. This black hole is not directly visible to our eyes, but its influence radiates outward across the entire electromagnetic spectrum. Radio waves, X-rays, and gamma rays pour from the galactic center, creating a bright and complex foreground that washes out the faint signals coming from the zone of obscuration. When astronomers aim their telescopes toward that hidden patch of sky, they are not just looking through dust and stars. They are also staring directly into the glare of our own galaxy's most violent core. The outflows from Sagittarius, a star, are not a steady glow. They erupt in flares and jets of high-energy particles, sometimes blasting material outward at nearly the speed of light. These eruptions produce intense bursts of radio and gamma-ray emission that can last for days or weeks. For any instrument trying to detect a distant galaxy or a faint gas filament behind the Milky Way, such a flare is like trying to read a book while someone shines a flashlight directly into your eyes. The noise created by the galactic center drowns out the whisper of structures billions of light-years away. Even in quieter periods, the steady glow from the black hole's surroundings, a diffuse halo of hot gas and relativistic electrons, adds a constant background hum that must be carefully subtracted from every observation. This is not a small problem. Some of the most promising areas for finding hidden galaxy clusters or the warm-hot intergalactic medium lie within a few degrees of the galactic center. Every measurement in that direction carries a contamination that is devilishly hard to remove. Researchers have developed sophisticated algorithms to model the emission from Sagittarius, a star, and its surroundings. But those models rely on assumptions about the black hole's activity history and the structure of the surrounding gas. A single unexpected flare can invalidate weeks of data. The challenge is compounded by the fact that the black hole influences the very gas and dust that creates the obscuration. High-energy outflows can heat and ionize the interstellar medium, changing how it absorbs and scatters light from background sources, so the same processes that make the zone so opaque are themselves shaped by the black hole at its heart. Until astronomers can fully disentangle the black hole's emissions from the signals they seek, many of the deepest mysteries of the obscuration will remain blurred. Every new observatory that operates in radio or gamma ray wavelengths, like the Event Horizon Telescope or the upcoming Cherenkov Telescope array, offers a chance to refine that subtraction. But for now, the supermassive black hole at the center of our galaxy remains both a beacon and a veil, a source of fascination and frustration that sits right at the heart of our quest to see what lies beyond. Beyond the glare of the galactic core, a different kind of emptiness awaits. Astronomers call it the local void, a vast region of space where galaxies are surprisingly scarce. This void sits just beyond our local group, the collection of galaxies that includes the Milky Way and Andromeda. It is not completely empty, but compared to the dense clusters and filaments that fill most of the universe, it is a desert. The local void stretches across roughly 60 million light-years, and its very existence shapes the motion of everything around it. When a galaxy finds itself at the edge of such a low-density region, the surrounding structures pull it in different ways, creating a gravitational dance that can be measured and mapped. Our own local group is being tugged away from the void, pushed by the slight overpressure of matter on the opposite side. This is one reason our galaxies are moving at about 600 kilometers per second toward the Great Attractor, but the void contributes its own subtle push. For decades, galaxy surveys have noted a striking lack of galaxies in the direction opposite the Great Attractor, a patch of sky that just happens to overlap with the Zone of Obscuration. The problem is that the void is largely hidden behind the Milky Way's dust, so its full extent remains uncertain. Early redshift surveys like the one carried out by the Hubble Space Telescope and later the 6-degree field survey have found only a handful of faint galaxies in that direction, far fewer than expected for a typical patch of the universe. This deficit is exactly what you would expect if the local void extends into the zone, swallowing up a large volume that should contain hundreds or thousands of galaxies. But because the dust blocks our view, we cannot tell whether the missing galaxies are truly absent or simply hidden in the foreground glare. If the void is as large as some models suggest, then its boundary with the surrounding superclusters could be a key driver of the peculiar motions we observe in nearby galaxies. Imagine a bubble of emptiness pressing against the wall of galaxies that contains the Norma Cluster and the Great Attractor. That pressure, combined with the gravitational pull of the wall itself, creates a complex flow that astronomers are still trying to untangle. Mapping the void's edge within the Zone of Obscuration would give us a much clearer picture of those forces. It would tell us exactly where the low-density region ends and the high-density structures begin. Without that map, our understanding of why galaxies move the way they do remains incomplete, like trying to read a river's current while ignoring the shape of the riverbed. A deeper kind of void may be imprinted on the oldest light in the universe. In 2004, the Wilkinson Microwave Anisotropy Probe, a spacecraft that mapped the faint afterglow of the Big Bang, revealed something unexpected. A patch of sky nearly 1.8 degrees across appeared slightly colder than its surroundings. This became known as the Cosmic Microwave Background Cold Spot, and for nearly 2 decades, astronomers have debated what caused it. The most compelling explanation involves a supervoid, a vast region of space where the density of matter is far lower than average. When light from the early universe travels through such a void, it loses a tiny amount of energy as it climbs out of the gravitational dip, leaving a cold imprint on the cosmic microwave background. That process is called the integrated Sachs-Wolf effect. The problem is that any supervoid large enough to create this cold spot would have to be enormous, perhaps hundreds of millions of light-years across. And the cold spot's location in the sky is deeply frustrating. it lies in the direction of the constellation Eridanus, which is right along the southern edge of the Zone of Galactic Obscuration. The same dust and stars that hide galaxy clusters and walls may also be concealing the very void that left its mark on the cosmic microwave background. If the supervoid is real, there should be a clear deficit of galaxies in that line of sight. Fewer galaxies means less matter, and less matter means a gravitational hole big enough to drain energy from passing photons. So astronomers have turned to infrared surveys, which can pierce through the dust better than visible light. The Wide Field Infrared Survey Explorer, or WISE, and the 2-micron All-Sky Survey have been used to count galaxies in the direction of the cold spot. Early results were tantalizing but inconclusive. Some studies found a mild deficit, but not enough to explain the full temperature drop. Others saw nothing unusual. The confusion comes partly because the foreground dust in that part of the zone is patchy and hard to model. It can mimic a galaxy deficit by obscuring faint sources. Or it can hide a real deficit by scattering light from nearby stars into the field. Every attempt to measure the void runs into the same wall of obscuration that blocks so many other investigations. Yet the stakes are high. If the cold spot is indeed caused by a supervoid, then we have found the largest known structure in the nearby universe, a cavity so enormous that it reshapes the oldest light we can detect. If it is not, then we may be seeing the first hint of something far stranger, perhaps a flaw in our standard model of cosmology or a signal from before the Big Bang. Either way, the answer lies behind the Milky Way, waiting for telescopes that can see through the glare of our own galaxy. Just a few degrees away from that cold spot, another cosmic puzzle hides in the dust. The Antlia cluster is one of the nearest rich galaxy clusters to us, yet it remains surprisingly poorly understood. Its position near the galactic plane places it just inside the outer fringe of the Zone of Obscuration, where the Milky Way's dust and stars dim and distort the light from its member galaxies. Optical telescopes have difficulty picking out individual galaxies against the bright foreground, and even infrared surveys struggle with the patchy extinction. As a result, the Antlia cluster has been studied far less than other clusters at comparable distances, like the Fornax or Virgo clusters. What astronomers have managed to piece together reveals a cluster with an unusual and dynamic history. The Antlia cluster does not have the smooth, symmetrical shape that many older clusters display. Instead, its galaxies are spread out in a messy, elongated structure, with multiple dense subclumps that suggest a recent, violent merger. Evidence from X-ray observations shows that the hot gas between the galaxies is not evenly distributed. There are regions of disturbed gas, shocks, and a faint bridge of hot matter connecting two main concentrations. This points to a collision between two smaller groups that are still in the process of combining into a single larger cluster, but the timing and scale of that merger remain unclear. Some models suggest it happened only a few 100 million years ago, a blink in cosmic time, which would make the Antlia cluster a living laboratory for studying how clusters grow through collisions. The most puzzling anomaly lies in the cluster's velocity dispersion. This is a measurement of how fast the individual galaxies are moving relative to the cluster's center. In a stable cluster, the velocity dispersion should match the total mass. Faster motions mean more gravity is needed to hold everything together. But in Antlia, the velocity dispersion is unusually high for the amount of visible matter. That discrepancy could mean there is a lot more dark matter present than expected, or it could indicate that the cluster is not yet in equilibrium. If the merger is recent, the galaxies may still be swinging on stretched orbits, giving a false impression of high speeds. Alternatively, the cluster might be pulling in material from a hidden filament of galaxies that extends into the obscured region behind the Milky Way. Without clear observations of that surrounding area, it is impossible to tell whether Antlia is a self-contained system or part of a larger, hidden supercluster. Better observations in the zone of obscuration could resolve these disagreements. If astronomers could map the full extent of the Antlia cluster and its surroundings in the infrared or radio, they could measure the true velocity dispersion of its galaxies and compare it to the gravitational pull from the hot gas and dark matter. They could also look for faint dwarf galaxies that might be falling into the cluster from the direction of the galactic plane, revealing the presence of a connecting filament. A dedicated survey with a telescope like the James Webb Space Telescope or the upcoming Nancy Grace Roman Space Telescope could peer through the dust and count the cluster's members with much higher accuracy. Until then, the Antlia cluster remains a messy, unresolved chapter in our understanding of how clusters form and evolve, and like so many other mysteries in this hidden region, the answers are sitting just out of sight, waiting for a clearer view. Could the Milky Way be carving a void right around its own disk? This idea might sound strange at first, but it comes from a growing body of research into how galaxies shape their own surroundings. For decades, astronomers assumed that the zone of obscuration is entirely an observational problem, a curtain of dust and stars that blocks our view. But some simulations of galaxy formation suggest there could be a real emptiness mixed in with that curtain, a genuine lack of galaxies along the galactic plane caused by the Milky Way itself. The mechanism behind this possible void is feedback. When massive stars live fast and die young, they explode as supernova. Those explosions blast gas and heavy elements outward at tremendous speeds. Over millions of years, repeated supernova and the fierce stellar winds from young hot stars can create a bubble of hot, thin gas that pushes away the surrounding material. In a galaxy like ours, this feedback is strongest in the disk, where star formation is most active. The energy from countless supernovae can sweep the interstellar medium clear of the cold, dense gas needed to form new galaxies. Now imagine what that means for any small, faint galaxies that might have been forming in the galactic plane region. The Milky Way's feedback could have prevented them from ever forming at all, or it could have stripped away their gas and left them as faint, nearly invisible remnants. This would create a genuine deficit of galaxies along the plane, a void that is not just a trick of the dust, but a real physical absence. Computer simulations of galaxy evolution, like those run in the Illustris and Eagle projects, show that feedback from a large disk galaxy can indeed create such a zone of reduced galaxy density. The effect is most pronounced for low-mass dwarf galaxies, which are easily disrupted or starved by the energy pouring out of the big galaxy. Yet testing this idea against the real sky is incredibly difficult. When we look toward the galactic plane, we see both dust and this possible void mixed together. An optical telescope sees nothing, but an infrared telescope might see enough stars to confuse the signal. A radio telescope, which can pierce dust more easily, might detect a few galaxies, but their numbers might still be lower than expected. Distinguishing between a genuine void and mere obscuration requires comparing observations across many wavelengths. For example, if a region appears empty in visible light, but shows a normal density of galaxies in far infrared or radio, then the emptiness is just dust. But if it appears empty in all wavelengths, even those that cut through dust, then a real void is likely. Surveys like the Arecibo Legacy Fast Alpha Survey, which mapped neutral hydrogen in radio, and the Herschel Space Observatory's infrared surveys have begun to probe the galactic plane. Early results show patches where the number of galaxies is indeed lower than expected, even after accounting for dust. But the data is still too sparse to say whether this is a true void or just statistical noise from the patchy foreground. Some researchers have proposed that the galactic plane void could extend for tens of millions of light years, a bubble blown by the Milky Way's past activity. If such a void exists, it would mean our galaxy has influenced the large-scale structure of the local universe far more than we thought. It would also mean that the zone of obscuration is not just a blank spot on our maps, but a region with its own story, shaped by the very galaxy we live in. The next generation of radio arrays, like the Square Kilometre Array, will be able to map the neutral hydrogen in that region with unprecedented sensitivity. They could detect dwarf galaxies so faint that they are invisible to all other telescopes, or they could confirm the emptiness. Either way, the answer will force us to rethink how galaxies and their surroundings interact, and it will remind us that even our own home can hide secrets in the most unexpected places. Hundreds of tiny galaxies should orbit the Milky Way, but we can only see a handful. This is the missing satellites problem, one of the longest-standing puzzles in modern astronomy. According to the leading model of how the universe works, the cold dark matter theory, our galaxy should be surrounded by several hundred small dwarf galaxies. These are faint, low-mass systems that contain only a few million stars, far fewer than the billions in a full-sized galaxy like our own. Yet when astronomers have scanned the skies, they have found only about 60 confirmed satellites around the Milky Way. The gap between prediction and observation is huge. For years, the simplest explanation was that these missing dwarfs are too faint to detect with current telescopes, but that answer has worn thin as surveys have grown deeper and wider. A more intriguing possibility is that many of these predicted satellites are simply hiding from view, concealed behind the thick disk of the Milky Way itself. The Zone of Galactic Obscuration covers a large swath of the sky, and that is exactly where many of these hypothetical dwarf galaxies would be located. If they exist, they would be faint and small, making them almost impossible to spot through the dense dust and stars of the galactic plane, but recent optical surveys have begun to chip away at that barrier. The Dark Energy Survey, or DES, which observed a large patch of the southern sky using a powerful camera in Chile, has discovered several new dwarf galaxy candidates in the last decade. Some of these are very close to the galactic plane, sitting in regions that older surveys had written off as hopelessly obscured. A few of these candidates, like DS1 and DS2, lie within a few degrees of the plane, exactly where the missing satellites would be expected. Another survey, Pan-STARRS, scanned the northern sky and added its own list of possible dwarfs, some of them lurking near the galactic equator. Each one of these discoveries adds a piece to the puzzle. But the numbers are still far too low. Computer simulations suggest that dozens, perhaps even 100 more dwarf galaxies could be hiding just behind the thickest parts of the disk, waiting to be found. Finding them would do more than just balance the books. It would give astronomers a way to test the properties of dark matter itself. The number and distribution of dwarf galaxies around the Milky Way are sensitive to the nature of the dark matter particle. If dark matter is warm rather than cold, for example, it would suppress the formation of the smallest halos, producing fewer dwarfs. If dark matter is self-interacting, the halos might be more diffuse and harder to see. Every hidden satellite that is discovered or conspicuously absent helps narrow down those possibilities. The problem is that the zone of obscuration is the hardest place to look. Optical surveys like DS and Pan-STARRS can only see a little ways into the disk before the dust becomes too thick. To go deeper, astronomers need infrared or radio telescopes that can see through the obscuration. The upcoming Vera Rubin Observatory, with its massive camera and deep survey of the entire southern sky, will push the limit further. It might uncover a dozen or more new dwarf galaxies behind the veil. And the square-kilometer array, once it is fully operational, could detect the neutral hydrogen gas in even the faintest dwarfs, revealing them no matter how much dust lies in front. The missing satellite problem is not about a failure of the dark matter model. It is about a failure of our view. The solutions are out there, behind the glare and the dust, waiting for telescopes that can finally see past the Milky Way's silhouette. A stream of neutral hydrogen gas, glowing faintly in radio waves, is moving in the wrong direction around the Milky Way. This is not a stray cloud drifting with the galactic flow. It is a counter-rotating stream, a current of gas that spins against the rotation of the entire disk. Astronomers have known for decades that such anomalous high-velocity clouds exist. They were first detected in the 1960s, when radio telescopes scanning the sky found patches of hydrogen speeding at hundreds of kilometers per second, far faster than the normal rotation of the galaxy. What makes these clouds so puzzling is that many of them, especially those lying in the zone of obscuration, have no visible counterpart, no stars, no glowing gas, nothing that shines in optical light. They are invisible to our eyes, yet they are there, massive reservoirs of neutral hydrogen moving on orbits that seem to defy the orderly rotation of the Milky Way. The most dramatic of these is a structure called the Smith Cloud, a high-velocity cloud that is plunging back toward the galactic disk. The Smith Cloud is about 11,000 light-years away and contains enough hydrogen to make 1 million suns. It is moving at roughly 300 kilometers per second, and it is on a collision course with the Milky Way's disk. In a few tens of millions of years, it will crash into the gas and dust of our galaxy, triggering a burst of star formation. But the Smith Cloud is just one example. Dozens of other high-velocity clouds dot the sky, and a large number of them are concentrated near the galactic plane, right in the heart of the zone of obscuration. Their origins remain a subject of intense debate. One leading theory suggests that these clouds are the tidal debris from past interactions with dwarf galaxies. When a small galaxy passes too close to the Milky Way, the immense gravitational pull can tear it apart, stretching its gas into long streams that wrap around the larger galaxy. Over time, those streams can become twisted and fragmented, forming the high-velocity clouds we see today. This idea is supported by the fact that some of these clouds are aligned with the orbits of known dwarf satellites, like the Magellanic Clouds. The Magellanic Stream, a long ribbon of gas trailing behind the large and small Magellanic Clouds, is a prime example of such tidal debris, but a second theory points to a more primordial source. Some of these clouds may be leftover gas from the formation of the Milky Way itself, clumps of pristine material that never collapsed into stars. These primordial clouds would be composed mostly of hydrogen and helium, with very few heavy elements. They would have been orbiting the galaxy since the earliest days, slowly falling inward, disturbed by the gravitational pull of passing structures. When astronomers measure the chemical composition of some high-velocity clouds, they find exactly that, a low abundance of metals, supporting the primordial origin idea. The problem is that the full distribution of these clouds remains unknown. The zone of obscuration is where many of them are predicted to exist, but we cannot see them in optical light, and radio observations are hampered by the bright emission from the galactic plane itself. The hydrogen gas in the Milky Way's disk glows so brightly in radio that it drowns out the faint signals from distant clouds. To detect them, astronomers must use sophisticated filtering techniques, separating the signal of the disk from the signal of the incoming clouds. Even then, the results are ambiguous. Some clouds appear to be approaching the galaxy, while others seem to be receding. Some are rotating with the disk, others counter to it. The patchy foreground makes it nearly impossible to map their true three-dimensional structure. There is even evidence that a large fraction of the gas in the zone of obscuration may be part of a massive, coherent ring of high-velocity clouds encircling the entire galaxy. This hypothetical structure, sometimes called the Fermi bubbles in gas or the galactic center molecular ring, could be far larger than any individual cloud we have catalogued. If that ring exists, it would be a major clue about the history of gas accretion and star formation in the Milky Way, and it would be hidden almost entirely behind the dust and stars of the zone. Every new survey with radio telescopes like the Green Bank Telescope or the Australian Square Kilometre Array Pathfinder adds a few more pieces to the puzzle. But the full picture remains blurry, a ghostly map of shadows and whispers. The high-velocity clouds are like messengers from the galaxy's past, carrying stories of collisions, accretions, and the slow dance of dark matter halos. Until we can see them clearly in the obscured region, their messages will remain half-read, tempting us with secrets just beyond our reach. One of those secrets takes the form of a gigantic ribbon of gas stretching across the southern sky. Astronomers call it the Magellanic Stream, and it is one of the most dramatic structures in our cosmic neighborhood. This stream is a long, thin trail of neutral hydrogen gas that arcs more than 100 degrees around the sky, nearly half the circumference of the visible heavens. It begins near the Large and Small Magellanic Clouds, two dwarf galaxies that orbit our Milky Way, and it extends far beyond them, trailing behind like the wake of a ship. For decades, the leading explanation has been that this stream was torn from the Magellanic Clouds by the gravitational pull of the Milky Way during a close encounter. As the dwarf galaxies swung past our own, the immense tidal forces ripped away their gas, stretching it into a long, thin tail that now wraps around our galaxy. That picture is supported by computer simulations, which show that such a tidal interaction could produce a stream matching the observed shape and velocity of the gas. But the story is not that simple. There is evidence that the Magellanic Stream contains two distinct components, one rich in heavy elements and one nearly pristine. That suggests a more complex origin, perhaps a combination of tidal stripping and the ram pressure of the Milky Way's halo of hot gas pushing against the clouds, a process that would also remove gas. The true age of the stream is uncertain. Some models suggest it formed during a single close pass a few 100 million years ago. Others argue that it is the product of a longer, more gradual interaction spanning several billion years. The key to resolving this debate lies in the part of the stream that cannot be seen from Earth. About a third of the Magellanic Stream passes directly behind the galactic plane, disappearing into the zone of obscuration. There, the dust and stars of the Milky Way completely block our view in visible and radio wavelengths, but that hidden section may hold the most critical information. If the stream is continuous and smooth, that would support a steady, long-term stripping process. If it shows breaks, gaps, or knots of dense gas, that would hint at a more violent, episodic history. The obscured portion might also contain the remnants of an older, fainter stream that was stripped even earlier, a fossil from a previous encounter that has since been stretched and mixed with the main flow. To see through the dust, astronomers must turn to ultraviolet light. The warm gas in the Magellanic Stream glows in ultraviolet wavelengths, especially in the light of ionized carbon and oxygen. These wavelengths are blocked by Earth's atmosphere, so they can only be observed from space. Instruments like the Hubble Space Telescope and the Far Ultraviolet Spectroscopic Explorer have already detected portions of the stream in front of distant quasars, using the quasar's light as a backlight to reveal the stream's composition and motion. But the hidden section behind the galactic plane has never been probed in this way, because there are no bright background quasars in that direction that shine through the dust. Future space-based ultraviolet observatories, such as the proposed Ultraviolet Explorer or a larger successor to Hubble, might be able to search for the faint ultraviolet emission from the stream itself without needing a background light source. That would allow astronomers to map the full extent of the Magellanic Stream, even through the thickest parts of the Zone of Obscuration. If they succeed, they will finally be able to read the complete story of how the Magellanic Clouds have interacted with our galaxy and how they will eventually merge with it. But for now, that story remains partially hidden, a long, silent ribbon of gas waiting for a telescope that can see its deepest secrets. Our galaxy is surrounded by ghostly rivers of stars, and many of them flow behind the very disk we call home. These are stellar streams, the shredded remains of smaller galaxies that the Milky Way pulled apart long ago. When a dwarf galaxy drifts too close to a much larger one, the immense gravitational tides stretch it into a long, narrow ribbon of stars that wraps around the bigger galaxy. Over hundreds of millions of years, the stream becomes so diffuse that it blends into the background of the night sky, visible only to the most sensitive telescopes. Astronomers have already discovered dozens of these streams around the Milky Way, each one a fossil record of a past merger. The Sagittarius Stream, for example, wraps around our galaxy in a great loop and contains the remnants of the Sagittarius dwarf spheroidal galaxy, which has been slowly dissolving into the Milky Way for billions of years. The Orphan Stream and the Cetus Stream are other examples, each telling a different chapter of our galaxy's violent history, but the full story is incomplete. Computer models of galactic accretion predict that several more streams should exist, and many of them are expected to cross the zone of galactic obscuration. These predicted streams would be incredibly faint, containing only a few tens of thousands of stars spread across a vast arc. The dust and stars of the Milky Way's disk act like a thick fog, dimming their light and making them blend into the overwhelming foreground of our own galaxy. Even specialized surveys, like the Sloan Digital Sky Survey and the Dark Energy Survey, which have discovered most known streams, have had to avoid the galactic plane entirely. The only way to find a stream behind the dust is to look in infrared light, which can pierce through the obscuring material. The Wide Field Infrared Survey Explorer, or WISE, and the 2-micron All-Sky Survey have mapped the entire sky in infrared. But their resolution and sensitivity are only good enough to detect the brightest streams. Fainter ones remain invisible, hidden in the noise of the galactic disk. This is a problem because knowing the complete set of stellar streams is crucial for understanding how the Milky Way built itself up over time. Every accretion event left a distinct mark on the galaxy's structure, altering its rotation, its dark matter halo, and its star formation history. The streams are the only direct evidence we have of those ancient collisions. Without a full map, our reconstruction of the Milky Way's past is like trying to read a history book with half the pages torn out. Some of the missing pages may contain clues about the most important mergers, including those that brought in the building blocks of our galaxy's bulge or thick disk. The streams that cross the zone of obscuration could be the remains of a massive satellite that was devoured long ago, a key episode in the formation of the Milky Way as we know it. They might also reveal the shape of the dark matter halo that surrounds our galaxy, because the orbits of the streams are sensitive to the gravitational pull of invisible matter. By tracing a stream that passes behind the galactic plane, astronomers could test whether the dark matter halo is spherical or flattened, a measurement that is almost impossible to make by any other means. The next generation of wide-field surveys, like the Vera-C, Rubin Observatory's legacy survey of space and time, will be able to see fainter stars and deeper into the infrared than ever before. It may finally peel back the curtain on these hidden rivers of stars. Every new stream discovered behind the zone of obscuration will be like finding a lost chapter in the biography of our galaxy, a chapter that has been waiting for us to learn how to read it. The spin of a galaxy is not a random toss of a cosmic coin. Astronomers have observed that in certain patches of the sky, the rotation axes of hundreds of galaxies point in surprisingly similar directions, as if some hidden hand had gently nudged them into alignment. This is not a small effect. Studies of the Sloan Digital Sky Survey have found that galaxies within large superclusters tend to have their spins aligned with the vast filaments that connect them. It is as though the cosmic web itself imprints a preferred orientation on the galaxies that form within its strands, yet the pattern is not uniform. In some regions, the alignment is strong, in others, it vanishes entirely. This unevenness raises a critical question. Is the alignment a universal property of structure formation, or is it merely a local quirk caused by the gravitational pull of a nearby massive object? The answer may lie hidden behind the Milky Way. The zone of obscuration contains thousands of galaxies whose spin axes have never been measured. If those hidden galaxies show the same alignments as the ones we can see, it would suggest that the effect is truly universal, woven into the fabric of large-scale structure. But if the hidden galaxies show random spins or alignments that contradict the pattern, it would force astronomers to reconsider the underlying mechanism. Perhaps the alignments are caused by tidal torques from a nearby supercluster or the flow of matter toward the Great Attractor. Without the obscured data, every claim about galaxy spin alignment is built on an incomplete sample. It is like trying to read a sentence with half the letters erased. Astronomers are now turning to radio telescopes, which can measure the rotation of a galaxy by detecting the Doppler shift of its neutral hydrogen gas, a signal that cuts right through the dust. The Australian Square Kilometre Array Pathfinder and the Milky Way telescope in South Africa are beginning to map the spins of galaxies in the zone, one by one. Early results are tantalizing. A few dozen galaxies show hints of alignment stretching across the observed region, but the sample is far too small to draw firm conclusions. Every new measurement adds a thread to the cosmic tapestry, and only by completing that tapestry will we know whether the hidden galaxies are dancing to the same tune as the rest of the universe. Until then, the alignment of galaxy spins remains one of those puzzles where the missing pieces are literally sitting behind our own galaxy, waiting for a clearer view. A different kind of light cuts through the dust, revealing something far more energetic. Gamma rays, the most powerful form of electromagnetic radiation, can travel straight through the thickest clouds of gas and dust that block our visible telescopes. When the Fermi Large Area Telescope began scanning the entire sky in gamma rays, it mapped the plane of the Milky Way in astonishing detail, but the map came with a surprise. The diffuse glow of gamma rays coming from the galactic plane is significantly brighter than what astronomers expected from the normal interactions of high-energy cosmic rays with the gas and starlight of our galaxy. Cosmic rays, which are fast-moving particles accelerated by supernova explosions, should collide with interstellar gas and produce a predictable amount of gamma-ray light. Yet the Fermi data shows an excess, a surplus of gamma rays that cannot be explained by those known processes alone. Some of that extra glow could be coming from faint, unresolved sources hidden behind the densest parts of the galactic plane. Every supernova remnant that has faded to invisibility in visible light still glows in gamma rays for tens of thousands of years. Pulsars, the rapidly spinning remains of dead stars, also emit a steady beam of gamma radiation. If dozens or even hundreds of such objects lie behind the dust, their combined emission would add up to a diffuse excess that Fermi sees as a uniform glow. The trouble is that the galactic plane itself is full of foreground sources that produce the same kind of signal. Young pulsars, active star-forming regions, and even the diffuse emission from the galactic halo all blend together into a confusing mix. Untangling which part of the excess comes from the hidden zone and which part comes from our own galaxy's familiar residents is like trying to listen to a single voice in a roaring crowd. Astronomers have tried to subtract the known foreground sources using models based on star formation rates and pulsar populations, but those models are only as good as our incomplete census of what lies nearby. Every new pulsar or supernova remnant discovered in the plane shifts the balance, revealing that some fraction of the excess was actually coming from a hidden object. The most intriguing possibility is that the gamma-ray excess may contain a signal from something truly exotic, such as the annihilation of dark matter particles. Dark matter is thought to clump densely in the galactic plane, and if it decays or annihilates, it would produce gamma rays with a specific energy signature. Some researchers have claimed to see a faint signal consistent with dark matter in the Fermi data, but the galactic foreground is so bright that the claim remains hotly debated. The hidden region behind the zone of obscuration could hold the key to settling that debate. If there is a patch of sky where the foreground is unusually low and the gamma-ray excess is still present, that would be strong evidence for a dark matter origin. But the very dust that hides galaxies also hides the true distribution of gas and cosmic rays that produce the foreground. Without a complete map of the galactic plane in other wavelengths, the interpretation of the gamma-ray excess remains a tangled knot. Each new observation with Fermi or with the future Cherenkov telescope array adds a few more threads to pull, but the full picture is still buried behind the glow of our own galaxy. The gamma-ray excess is a reminder that even in the most energetic light we can detect, the zone of obscuration keeps its secrets close, daring us to find a way to see through the glare. A giant arc of radio light rises from the galactic plane, stretching halfway across the sky. Astronomers call it the North Polar Spur, a vast swath of glowing gas that emits powerfully in both radio and X-rays. It begins near the center of the Milky Way and curves upward, reaching far into the northern hemisphere of our galaxy. The structure is enormous, spanning tens of degrees, yet its true shape has always been difficult to pin down. That is because a significant portion of the spur extends into the zone of galactic obscuration, where the dense dust and stars of the galactic disk block our view. Even at radio and X-ray wavelengths, which normally cut through dust, the foreground emission from the galactic plane itself creates a confusing haze. As a result, the North Polar Spur appears as a partial silhouette, its far end lost in the glare of our own galaxy. The origin of this gigantic feature is one of the longest-running debates in galactic astronomy. For decades, the most popular explanation was that the spur is the remnant of a nearby supernova, a massive stellar explosion that occurred only a few hundred light-years away. In that picture, the expanding shell of hot gas, still glowing in X-rays, would be the bubble blown by the dying star, but the spur is too large and too energetic to be a typical supernova remnant. Its shape is also too regular, a smooth arc rather than a chaotic shell. Another theory suggests that the North Polar Spur is actually a galactic outflow, a stream of hot gas being blown out from the center of the Milky Way by the combined energy of star formation and the supermassive black hole. This would connect it to another mysterious structure, the Fermi bubbles, two enormous lobes of gamma-ray and radio emission that extend above and below the galactic plane. The spur might be the edge of one of those bubbles, a shock front where the outflowing gas collides with the surrounding halo. Yet a third idea holds that the spur is not a single object at all, but a superposition of multiple unrelated features along the same line of sight. A nearby shell of gas, a distant filament of the galactic halo, and a foreground cloud of dust could all align by chance to create the illusion of a single giant arc. Each of these hypotheses makes different predictions about the spur's distance, temperature, and motion. The problem is that the part of the spur buried in the zone of obscuration holds the crucial evidence. If astronomers could map its full extent through the dust, they could measure its expansion rate or its connection to the Fermi bubbles, but that hidden section remains stubbornly out of reach. New radio surveys like the Galactic Plane Survey from the Australian Square Kilometre Array Pathfinder are beginning to peel back that obscuration, revealing a faint continuation of the spur's emission deep in the galactic plane. Yet the signal is weak, and the foreground confusion is immense. Every new observation brings us a little closer to deciding which origin story is correct. But for now, the North Polar Spur remains a beautiful and puzzling ghost, half seen and half imagined, a reminder that even the most prominent features of our own galaxy can keep their origins hidden behind the very stars they rise from. Two colossal bubbles of gamma-ray light rise from the center of our galaxy. They were discovered in 2010 by the Fermi Gamma-Ray Space Telescope, and they are among the most dramatic and mysterious structures ever detected in the Milky Way. Each bubble extends roughly 25,000 light-years above and below the galactic plane, forming a pair of enormous lobes that together span more than half the diameter of the galaxy itself. These are the Fermi bubbles, and their edges reach directly into the zone of galactic obscuration. In fact, a significant fraction of each bubble lies behind the thickest parts of the galactic disk, hidden from our view in visible light, but glowing brightly in gamma rays and radio waves. The bubbles are not empty. They are filled with high-energy particles, electrons and positrons moving at nearly the speed of light, and they glow with a faint but distinct gamma-ray signal. As these particles stream outward, they collide with the gas and magnetic fields of the galactic halo, creating shock fronts and heating the surrounding material. Those interactions generate additional radio and X-ray emission, which astronomers have mapped in detail using observatories like the Planck satellite and the Chandra X-ray Observatory. The resulting picture shows that the bubbles are not perfectly smooth. They have internal structures, filaments, and knots of brighter emission, suggesting that the outflow that created them was not a single, steady event, but a series of powerful bursts or a sustained wind that varied over time. That raises the central question: what powered these giant bubbles in the first place? There are two leading ideas, and they point to very different histories for our galaxy. The first theory argues that the bubbles were blown by a sudden, violent outburst from the supermassive black hole at the center of the Milky Way, Sagittarius, a star. In this scenario, the black hole went through a period of intense activity several million years ago, consuming large amounts of gas and launching powerful jets and winds that punched through the galactic disk and expanded into the halo. That kind of event would have been bright enough to be seen across the universe, a brief but brilliant flash in our galaxy's past. The second theory suggests that the bubbles are instead the product of a massive burst of star formation near the galactic center. When thousands of massive stars form in a short time, they produce fierce stellar winds and eventually explode as supernova. The combined energy from those explosions can drive a hot, fast-moving outflow that rises above the plane, carving out the bubbles over tens of millions of years. This is similar to the process that creates galactic winds in many other galaxies, but on a much larger scale inside the Milky Way. Both explanations are plausible, and both have supporting evidence. The black hole model is favored by the bubble's sharp, well-defined edges, which resemble the shock fronts seen in jets from active galaxies. The star formation model is supported by the bubble's internal structure, which matches simulations of a stellar-driven wind. The key to breaking the tie may lie in the part of the bubbles that is hidden behind the zone of obscuration. If astronomers could map the full shape and emission of the bubbles where they cross the galactic plane, they could measure the total energy contained within them and how that energy is distributed. A black hole-driven outburst would likely produce a more concentrated, energetic core, while a star formation-driven wind would be more diffuse and spread out. The obscured region also holds clues about the interaction between the bubbles and the dense gas of the galactic disk. That interface is crucial for understanding how much of the bubble's energy is absorbed or redirected, and it is almost entirely hidden from our view. Recent observations with radio telescopes like the Sgr A have begun to peer through the dust, revealing previously unseen filaments of radio emission that connect the bubbles to structures in the galactic plane. Those filaments may be the fossil remnants of the outflow, carrying the signature of its origin, but the picture remains incomplete. The Fermi bubbles stand as a monument to a dramatic event in our galaxy's past, an event so powerful that it still glows across the entire sky. And yet, the very force that created them may also be hiding the final pieces of the puzzle, buried in the same veil of dust and stars that keeps so many other secrets locked away. What we learn from those hidden regions will not only tell us how the bubbles formed, but will also reveal a chapter of the Milky Way's history that has been waiting, silently, for a telescope that can finally see through the glare. Our entire local group is racing through space at 600 kilometers every second. This is not a random drift. It is a measured velocity, read directly from the cosmic microwave background, the faint afterglow of the Big Bang. When we compare the temperature of that background in one direction versus another, we see a clear dipole pattern, a hot spot ahead and a cold spot behind. That pattern tells us that the Sun, the Earth, and every star in the Milky Way and Andromeda are being dragged toward a point in the southern constellation of Centaurus at an astonishing speed. For decades, astronomers assumed that this motion was driven entirely by the pull of the Great Attractor, that hidden concentration of mass behind the Zone of Obscuration. They calculated the gravitational tug from all the galaxies and clusters we could see in that direction, including the Norma Cluster and the surrounding supercluster, and it seemed like a good match. But better measurements and more detailed surveys have revealed a troubling gap. The total mass we can account for, even including the Great Attractor and its surrounding walls, is not enough to explain the full 600 km/s drift. Something else is pushing or pulling, and it is missing from our maps. That missing influence points directly back to the Zone of Obscuration. Somewhere behind the dust and stars, there must be an even greater concentration of matter, a hidden supercluster or a dense filament of galaxies that adds its own gravitational attraction. But there is another possibility, one that flips the entire picture. Instead of only being pulled forward, the local group might also be pushed from behind. This is the idea of the dipole repeller. Imagine being in a crowd where everyone on one side is shoving you away, while everyone on the other side is pulling you toward them. Your motion is a combination of the push and the pull. In the universe, a large void, a region of extremely low density, can act like a push. The matter around it is slightly more dense, and the universe naturally expands from underdense regions toward overdense ones. If a significant void lies in the direction opposite the Great Attractor, it would be effectively repelling the local group, adding to the net motion toward the other side. Early surveys of the sky opposite the Great Attractor, a region that also falls within the Zone of Obscuration, have found hints of just such a void. It is called the dipole repeller, and if it exists, it could account for roughly half of our measured velocity. But confirming its size and shape requires mapping the distribution of galaxies in that hidden patch of sky, a task that has barely begun. Every new galaxy discovered in that direction, or every empty patch confirmed, brings us closer to understanding why our local group moves the way it does. The answer will come from telescopes that can see through the Milky Way, peeling back the veil to reveal not only the hidden attractors, but also the unseen empties that shape the very flow of the local universe. The Hubble Space Telescope, arguably the most famous eye on the universe, has a deliberate blind spot. It almost never points near the crowded plane of our Milky Way. The reason is simple. The same dust and bright stars that hide distant galaxies also threaten to damage Hubble's sensitive instruments. A single bright star can saturate its detectors, ruining an observation. So mission planners carefully avoid aiming anywhere close to the galactic plane. That means the Hubble, which has given us some of the deepest images of the cosmos, has purposely overlooked nearly a fifth of the entire sky. This is not a flaw in the telescope itself. It is a practical necessity, but the result is a significant bias in our surveys. Every catalog of galaxies built from Hubble data and from most ground-based optical telescopes shares the same gap. The Zone of Galactic Obscuration is a vast empty wedge in our cosmic maps, not because nothing is there, but because telescopes were never designed to look that way. This bias affects far more than just pretty pictures. It skews our understanding of galaxy distribution, of large-scale structure, and of the very motions of nearby galaxies. When astronomers measure the density of the universe in our local neighborhood, they are forced to extrapolate across this missing region. Every calculation of the Great Attractor's pull, every model of the local group's movement, is built on an assumption about what lies behind the veil. And that assumption could be wrong. To fill in the gap, astronomers have turned to telescopes that see in different wavelengths. The Wide Field Infrared Survey Explorer, or WISE, scanned the entire sky in infrared, a type of light that cuts through dust much better than visible light. WISE revealed thousands of previously hidden galaxies, especially those that are bright in the mid-infrared. But even infrared has limits. Very cold or very distant galaxies can be too faint for WISE to detect. Radio telescopes have become the other essential tool. The Australian Square Kilometre Array Pathfinder, known as ASKAP, is a network of radio dishes designed to survey large areas of sky quickly. Radio waves pass through dust almost completely, and ASKAP can map the neutral hydrogen gas in galaxies even when their stars are invisible. Its survey of the southern sky, called the ASKAP Evolutionary Map of the Universe, has already begun to peel back the obscuration, discovering thousands of galaxies behind the galactic plane. Each new detection is like adding a piece to a puzzle that has been missing for decades. Yet the process is slow. Radio surveys take time, and the data is complex to analyze. For every galaxy ASKAP finds, many fainter ones remain hidden. The combination of infrared and radio efforts is slowly filling the blind spot, but it is a painstaking task. Every new source of light, every new wavelength, adds a layer to our understanding. The great observatories of the past had good reasons for avoiding the galactic plane. But now, as we build the next generation of telescopes, we are finally learning to look where they would not, and what we find there may change the way we see the entire universe around us. The blind spot is shrinking, but it is not gone yet, and in that remaining darkness, answers to some of the biggest cosmic questions may still be waiting. Dark matter simulations reveal a vast cosmic web of filaments stretching across the universe, but we cannot see most of them. These filaments are the invisible scaffolding on which galaxies form and cluster together. In the standard model of how the cosmos took shape, dark matter, the mysterious substance that makes up most of the mass in the universe, collapsed into a network of long, interconnected strands. Ordinary matter then fell into those strands, cooling and forming stars and galaxies. So wherever we see a dense line of galaxies, we know we are looking at a dark matter filament. But the filaments themselves are invisible. They emit no light. We can only infer their presence by the galaxies that trace them. That is where the zone of galactic obscuration becomes a critical blind spot. If half the galaxies in a particular filament are hidden behind the Milky Way's dust and stars, then the entire filament might be missing from our maps. Some of the largest predicted filaments, like the one that connects the Norma Cluster to the Shapley supercluster, may cross directly through the obscured region. We have only faint hints that they exist, based on the few galaxies we can spot in infrared or radio light. But the full shape, length, and mass of these dark matter structures remain unknown. To see them directly, astronomers would need to map the gravitational pull of the dark matter itself without relying on the galaxies that trace it. There is a way to do that, a technique called weak gravitational lensing. When the light from a distant galaxy passes near a massive object, like a dark matter filament, the gravity of that object bends the path of the light slightly. The image of the distant galaxy becomes subtly distorted, stretched by a tiny fraction of a degree. by measuring the shapes of millions of background galaxies, astronomers can reconstruct the distribution of mass that is causing the distortions. This is how we have mapped dark matter halos around clusters and even found filaments linking them, but only in regions of the sky that are unobscured. The problem in the zone of obscuration is twofold. First, the Milky Way's own stars and dust produce a strong foreground that scrambles the shapes of background galaxies. The distortion from our own galaxy can look almost identical to the weak lensing signal from a distant filament. Second, the number of background galaxies visible behind the thickest parts of the zone drops dramatically. There are simply not enough distant galaxies to measure their shapes with statistical significance. So although weak lensing is the most direct way to see dark matter, it fails in the very place we need it most. Astronomers are trying to overcome this by using multiple colors of infrared light to separate the foreground stars from the background galaxies. By comparing images taken at different wavelengths, they can identify which objects are nearby and which are far away. Then they subtract the light from the nearby ones and measure the shapes of the remaining distant galaxies. This process is computationally intensive and requires extremely deep observations. A few pilot studies using data from the Hubble Space Telescope and ground-based infrared surveys have managed to obtain weak lensing signals in small patches near the edge of the zone. Those early results show hints of a filament extending from the Norma Cluster toward a region of empty space, but the signal is too weak to confirm. The upcoming Nancy Grace Roman Space Telescope, with its wide field of view and infrared sensitivity, will be able to survey large swaths of the obscured sky. It may finally map the dark matter filaments that lie behind the Milky Way, revealing the hidden skeleton of the cosmos. Until then, the cosmic web remains incomplete, with its strongest strands cut short by the very galaxy we call home. Every filament we uncover will not only fill a gap in our maps, but also test the predictions of dark matter theory in a region that has been out of reach for decades. The answers are there, written in the subtle bending of light, waiting for a telescope that can see past the glare. Hundreds of thousands of galaxies are completely hidden behind the Milky Way's thickest dust. That estimate comes from combining what we know about the average density of galaxies in the universe with the size of the zone of galactic obscuration. If you take a typical patch of sky far from the galactic plane and count every galaxy down to a certain brightness, you get a number. Then you imagine that same patch placed directly behind the densest parts of the Milky Way disk. The dust and stars there block so much light that even the brightest galaxies become invisible to optical telescopes. The tally of missing galaxies runs into the hundreds of thousands, perhaps more. Think of it this way: the entire night sky contains roughly 5,000 stars visible to the naked eye. The hidden galaxies behind the galactic plane outnumber those stars by a factor of at least 20. Yet we cannot see a single one of them without special instruments. Deep near-infrared surveys have begun to chip away at that invisibility. The VISTA variables in the Via Lactea survey, known by its abbreviation VVV, used a powerful telescope in Chile to scan the southern galactic plane in infrared light. Infrared wavelengths pass through dust much more easily than visible light, so VVV could see stars and galaxies that were previously completely hidden. The survey turned up hundreds of new star clusters and millions of individual stars, but it also revealed a surprising number of galaxies lurking just behind the thinnest patches of dust. Some of those galaxies were bright enough to be catalogued for the first time, but the thickest dust clouds remained impenetrable even to VVV. The most obscured parts of the galactic plane, regions where the dust extinction is hundreds of times greater than the average, still hide the vast majority of those hundreds of thousands of galaxies. Photons from those distant worlds are absorbed, scattered, and dimmed so severely that they never reach any telescope on Earth. Only radio waves, which can travel through almost anything, might eventually detect the hydrogen gas in those galaxies. But radio surveys take time and need large arrays to achieve the sensitivity required. The census of hidden galaxies is far from complete. Why does that matter? Because the number and distribution of galaxies in the local universe is a direct test of our models of galaxy formation. Computer simulations predict how many galaxies should exist at each mass and brightness, based on the initial conditions of the Big Bang and the physics of dark matter and gas. If we find significantly fewer galaxies than expected in the zone of obscuration, it might mean that something about our models is wrong. Perhaps galaxy formation is suppressed near massive galaxies like the Milky Way, or perhaps the dust is so thick that even radio surveys miss many targets. On the other hand, if we eventually uncover a huge population of faint galaxies behind the plane, it could bring our local census into perfect agreement with simulations, confirming that we have finally accounted for all the missing pieces of the cosmic web. Every new hidden galaxy that appears in an infrared or radio image adds a data point to that test. The work is slow, painstaking, and often frustrating, but the stakes are immense. We are not just filling in a blank spot on a map. We are checking whether the story of how galaxies built themselves is the same in the most obscured corner of the sky as it is everywhere else. And until we complete that census, the biggest blind spot in astronomy will remain a silent challenge to everything we think we know about the universe. The oldest light in the universe carries a strange signature. When cosmologists look at the cosmic microwave background, the faint afterglow of the Big Bang, they see tiny temperature variations across the sky. These variations are the seeds of all structure we see today, but on the very largest angular scales, something is off. The fluctuations are weaker than our best models predict. This is known as the lack of power at large angular scales, and it has been a persistent puzzle for decades. One of the most intriguing explanations is that a giant void, an enormous region of space with far fewer galaxies than average, is sitting relatively close to us in cosmic terms. Such a void would alter the path of the CMB photons passing through it. As those photons climb out of the gravitational dip, they lose a little energy, creating a slight cold imprint across a broad patch of sky. That imprint could suppress the apparent power on large scales, exactly matching what we observe, but there is a catch. Any void large enough to produce this effect would have to be hundreds of millions of light years across, and its location would be critical. It would need to lie along our line of sight to the CMB, and the most likely place for such a void to hide is, of course, behind the zone of galactic obscuration. Our own galaxy blocks the view of that entire region, so we cannot easily see whether a vast emptiness actually exists there. The only way to test this idea is to carry out deep galaxy surveys in the obscured zone, using infrared and radio telescopes that can cut through the dust. If a giant void is present, we should find far fewer galaxies in that direction than in any other part of the sky. A few early surveys have hinted at a deficit, but the data is still too shallow and too patchy to be sure. Every new galaxy that appears in a deep survey of the zone brings us closer to confirming or ruling out this hypothesis. If the void is real, It would solve a long-standing puzzle in cosmology and reveal a structure so immense that it literally reshapes the oldest light we can detect. If it is not there, then the anomaly in the CMB must have a different origin, perhaps from the very early universe or from unknown physics. Either way, the answer is waiting in the hidden part of the sky. The zone of obscuration holds the key to understanding why the largest scales of our universe look the way they do. Ring of gamma ray burst stretches across the sky, and part of it may be hidden behind our galaxy. In 2015, a team of astronomers reported something astonishing. They found 9 gamma-ray bursts, the most powerful explosions in the universe, arranged in a nearly perfect circle spanning about 5 billion light-years. The odds of such an alignment happening by chance were calculated to be less than 1 in 10,000. This structure, if real, would be one of the largest known patterns in the cosmos, rivaling the Great Walls and supervoids. But the controversy began almost immediately. Gamma-ray bursts are rare events, and the sample was tiny. Other researchers argued that the apparent ring could be a statistical fluke, a random clustering of points that only looks ordered by chance. The debate has continued ever since, with no clear resolution. What makes the case even harder to settle is that a significant portion of that hypothetical ring falls directly into the zone of galactic obscuration. The Milky Way blocks our view of the gamma-ray bursts that might complete or disrupt the pattern. If there are more bursts lying behind the dust, either confirming the ring or breaking it apart, we cannot see them. The satellites that detect gamma rays, like the Swift Observatory and the Fermi Gamma Ray Space Telescope, are not blocked by dust. Gamma rays cut through the galactic plane easily. But the bursts themselves are brief and unpredictable. No one knows when or where the next one will flash. To prove or disprove the ring, astronomers would need a much larger catalog of bursts from that direction. That requires time and patience, and the zone of obscuration will keep withholding half the evidence for years to come. The ring remains a tantalizing possibility, a hint that the largest structures in the universe might be even more orderly than we think, or a reminder that our small sample sizes can fool us into seeing patterns that are not truly there. Only more data, collected from behind the veil of our own galaxy, will tell. Galaxy clusters are moving in ways our best models cannot fully explain. These are vast collections of hundreds or thousands of galaxies, bound together by gravity, and they should be drifting slowly with the expansion of the universe. But when astronomers measure their velocities relative to the cosmic microwave background, they find that entire clusters are streaming in coherent flows across distances of hundreds of millions of light years. These are not random motions, they are organized currents, like a great river sweeping everything along, and they are aimed toward a specific patch of sky. That patch is the zone of galactic obscuration, the standard model of cosmology, known as lambda cold dark matter, predicts the expected scale and strength of such bulk flows. According to the model, the gravitational pull of the largest structures, superclusters and voids, should produce these flows, but only up to a certain limit. Beyond about 100 megaparsecs, the flows should weaken because the universe becomes smooth on those scales. Yet observations tell a different story. Surveys of galaxy clusters out to several hundred megaparsecs have found that the bulk motions are surprisingly strong and coherent, far exceeding what the model allows. Some of the most powerful flows are directed straight into the hidden region behind the Milky Way. This mismatch has become known as the bulk flow anomaly. It suggests that something massive, something we cannot see, is pulling on these clusters from far beyond the local supercluster. The zone of obscuration is the most likely hiding place for that unseen attractor. If a large concentration of mass, perhaps a supercluster or a filament of dark matter, lies in that direction, its gravitational tug could be the engine driving these giant currents. But the Standard Model already accounts for the known distribution of matter in the nearby universe. Adding a hidden structure large enough to explain the flows would require that structure to be enormous, perhaps the most massive object within 1 billion light-years. If such a structure exists, it would challenge the fundamental assumptions of the Standard Model. It would mean that the universe on the largest scales is more clumpy and less smooth than we thought, or that gravity operates differently over those vast distances. On the other hand, if new surveys of the zone of obscuration fail to find any hidden mass, then the bulk flow anomaly would become even more puzzling. It would force cosmologists to reconsider the model itself, perhaps pointing to exotic alternatives like modified gravity or the influence of unknown forces. The key is to map the mass distribution behind the galactic plane with enough precision to see whether a hidden attractor is actually there. This requires combining galaxy counts with gravitational lensing and measurements of the peculiar velocities of galaxies in the region. Each new radio or infrared survey adds a few more points to that map. The more complete the map becomes, the clearer the picture of these coherent flows will be. Every hidden cluster or filament we uncover could either confirm the Standard Model or push it to its breaking point. The answer is waiting in that obscured patch of sky, where the largest currents of the cosmos converge and where the future of cosmology may be decided. These high-velocity clouds are not like any normal cloud you would see in the sky. They are vast streams of atomic hydrogen gas, moving at hundreds of kilometers per second, yet they contain no stars, no glowing nebulae, nothing that shines invisible light. Astronomers first detected them in the 1960s using radio telescopes, which are sensitive to the faint 21-centimeter line emitted by neutral hydrogen. The clouds appeared as unexpected patches of emission, often far from the galactic plane, and their velocities were startling. They did not follow the orderly rotation of the Milky Way. Instead, they were falling toward it, or in some cases, flying away, as if they had been flung by some ancient cosmic event. The mystery deepened when astronomers tried to see what these clouds looked like in optical light. They aimed the biggest telescopes toward the clouds' positions, expecting to find faint dwarf galaxies or at least a few stars, but in most cases, they found nothing. The clouds were ghostly, invisible to every instrument except radio receivers. That absence of stars is the central puzzle. If these clouds are made of normal gas, the same stuff that forms stars in our galaxy, then why have they not collapsed into stars during their long journey through space? The leading explanation is that the clouds are simply too diffuse. Their density is so low that gravity cannot overcome the internal pressure, so they remain as tenuous gas, never igniting star formation. But that answer only raises another question. Where did they come from? The most popular theory is that many of these high-velocity clouds are the tidal debris from past interactions between the Milky Way and its smaller satellite galaxies. When a dwarf galaxy like the Sagittarius Dwarf or the Magellanic Clouds passes close to our galaxy, the immense gravitational forces can pull long streams of gas away from the dwarf, stretching them into thin filaments. Over time, those filaments break apart into individual clouds, each one carrying the memory of its origin. This would explain why some clouds are rich in heavy elements, the chemical fingerprints of processed material from a galaxy, while others are nearly pristine, made mostly of hydrogen and helium. Those pristine clouds might be leftover gas from the formation of the Milky Way itself, clumps that never managed to fall into the disk and form stars. They would be essentially primordial, unchanged since the early universe, and here is where the zone of galactic obscuration enters the story. A large fraction of these high-velocity clouds are located at low galactic latitudes, right in the thick of the Milky Way's dusty plain. That is no coincidence. The galactic plane is where most of the tidal interactions happen, and it is also where the obscuration is densest. The result is that many of these clouds cannot be studied in optical wavelengths at all. Their stellar content, if any, is completely hidden behind the dust. Even in radio, the foreground emission from the Milky Way's own hydrogen gas creates a noisy background that makes it hard to measure the cloud's exact distances and velocities. Some astronomers have proposed that a few of these hidden clouds might be dark galaxies, objects made almost entirely of gas and dark matter, with so few stars that they are invisible to conventional telescopes. If such dark galaxies exist, they would be the missing link between dwarf galaxies and the diffuse gas in the intergalactic medium. But proving that a particular cloud is a dark galaxy is extremely difficult. It requires ruling out every other explanation, including tidal debris and chance alignments. The controversy is alive and unresolved. Every new radio survey that peers into the obscured region adds a few more clouds to the catalog, and each new cloud brings the same question: is this the remnant of a destroyed galaxy, a fossil from the early universe, or something entirely new? The answers are hidden behind the same dust that obscures so much else, waiting for a telescope that can see through the glare and reveal the true nature of these ghostly messengers. Magnetic fields are another invisible force threading through the zone of galactic obscuration, and they are just as mysterious as the dark matter and hidden galaxies. These fields are not something we can see with our eyes, but they have a powerful influence on everything that moves through them, especially cosmic rays, those high-energy particles that zip across the galaxy at nearly the speed of light. When cosmic rays encounter a magnetic field, they are deflected and scattered, their paths twisted into spirals by the invisible lines of force. In the dense, dusty regions of the galactic plane, the magnetic fields are thought to be especially strong and tangled, shaped by the turbulent gas and the shockwaves from exploding stars. But mapping those fields is a nightmare for astronomers because of a phenomenon called Faraday rotation. When polarized light from a distant radio source passes through a magnetized cloud of gas, its angle of polarization rotates, twisting by an amount that depends on the strength of the field and the density of free electrons along the line of sight. By measuring how much the polarization has rotated, scientists can in principle reconstruct the magnetic field strength and direction. But behind the thickest parts of the Milky Way, the signal is scrambled. The dust and the complex gas distribution create multiple layers of rotation, each one adding its own twist, until the original polarization is lost in a jumble of overlapping effects. The result is that the magnetic fields in the zone of galactic obscuration are among the worst mapped in the entire sky. Even the most sophisticated surveys, like those from the Planck satellite and the Global Magneto-Ionic Medium Survey, have only been able to produce rough, average maps. They show that the field is generally aligned along the spiral arms of the galaxy, but with many local anomalies. There are regions where the field seems to flip direction, or where it becomes exceptionally strong, perhaps because of nearby supernova remnants or the outflow from the galactic center. These details matter because the magnetic field affects how we interpret almost every other observation in the zone. It alters the propagation of cosmic rays, which in turn shape the gamma-ray emission we see from the galactic plane. It changes the polarization of the faint radio galaxies behind the dust, making it hard to tell whether their signals are intrinsic or twisted by our own galaxy. It even influences the formation of stars by regulating the collapse of gas clouds. Getting a clear picture of the magnetic field behind the veil is not just a niche curiosity. It is a prerequisite for understanding the large-scale structure of the Milky Way and the processes that drive its evolution. Every step we take toward untangling those invisible threads brings us closer to reading the hidden script of the galaxy, a script that is written in the bending of light and the twisting of radio waves, waiting for a telescope that can see through the magnetic fog. Radio surveys near the galactic plane are uncovering objects that defy easy explanation. Telescopes like the Very Large Array Sky Survey, known as VLAS, and the Australian Square Kilometre Array Pathfinder, or ASKAP, have been scanning the skies at radio wavelengths, which pass right through the dust that blocks visible light. What they have found in the Zone of Galactic Obscuration is a growing collection of strange, unidentified sources. Among the most puzzling are the odd radio circles, or ORC, faint rings of radio emission that appear as nearly perfect circles in the sky. The first few were discovered in 2019, and since then, a handful more have been found. They are enormous, spanning hundreds of thousands of light years across, yet they have no obvious counterpart in any other wavelength. No galaxy cluster, no supernova remnant, no known object matches their shape or size. Astronomers have proposed several explanations, from the shockwaves of colossal explosions to the outflow from a supermassive black hole, but none fit perfectly. The trouble is that these ORCs lie in the obscured region, and without an optical or infrared identification, their nature remains a complete mystery. They are just the tip of the iceberg. Radio surveys have turned up hundreds of other sources near the galactic plane that emit brightly at radio frequencies but have no visible star or galaxy at their location. Some might be distant galaxies with their optical light completely blocked by the Milky Way dust. Others could be new classes of astronomical phenomena that we have never seen before, perhaps related to exotic objects like magnetars or the remnants of ancient gamma-ray bursts. Every new source forces astronomers to ask the same question: is this something we already know, hidden behind the dust, or is it something entirely new? The difficulty of obtaining optical identifications is the main bottleneck. Even the most powerful optical telescopes, like the Hubble Space Telescope or the upcoming Vera Rubin Observatory, cannot see through the thickest parts of the galactic plane. So these radio sources remain unidentified, their true nature locked behind the same veil that hides so much else. Each one is a potential discovery waiting to be claimed, a clue to a puzzle that can only be solved with more observations at other wavelengths, especially infrared and X-ray, which can cut through the dust. The Zone of Obscuration is not just a blank spot on our maps. It is a frontier where the familiar rules of astronomy break down and where the unknown waits, glimmering faintly in the radio static, daring us to find a way to see what lies behind the glare. Our own galaxy's spiral arms are partly hidden behind the same dust that veils distant galaxies. The Milky Way is a barred spiral, with 4 major arms curling out from a central bar. These arms are not solid structures but regions of higher density where gas and dust collect, triggering the birth of new stars. Sprinkled along the arms are giant molecular clouds, vast complexes of cold gas and dust that are the cradles of stars. Some of the most famous ones, like the Orion Molecular Cloud or the Sagittarius B2 cloud, have been studied in detail, but large portions of the outer arms, especially those on the far side of the galaxy, lie behind dense lanes of dust that block visible light entirely. Even our own galaxy, the one we live inside, has regions we have never seen directly. Astronomers have known about this blind spot for decades. The classic map of the Milky Way, based on optical observations of stars and nebulae, is heavily skewed toward the near side. The far side of the galaxy, where the Perseus arm wraps around the far side of the galactic center, is almost invisible in optical light. The same is true for the outer reaches of the Scutum Centaurus arm, which extends into the thickest part of the galactic plane. To map these hidden structures, astronomers turn to radio waves. Neutral hydrogen gas, or HI, emits a faint signal at a wavelength of 21 centimeters, a frequency that passes through dust almost unaffected. By scanning the sky at that frequency, radio telescopes can build a three-dimensional picture of the galaxy's gas distribution, using the Doppler shift of the signal to measure the gas's velocity and distance. Carbon monoxide, or CO, is another key tracer. It is the most common molecule after molecular hydrogen, and it glows brightly at millimeter wavelengths, revealing the locations of the dense clouds where stars form. Surveys like the Galactic Ring Survey and the Hi-4Pi survey have used these tracers to map large swaths of the Milky Way, but the Zone of Galactic Obscuration remains a major gap in these maps. In the thickest parts of the galactic plane, the signal from faraway gas is either absorbed by foreground clouds or drowned out by the bright emission from nearby material. The result is that our model of the galaxy's spiral structure is uncertain for about a quarter of the disk. Some models suggest that the outer Perseus arm continues smoothly behind the galactic center, while others show it breaking into fragments or merging with another arm. The location and shape of the Norma arm, which lies on the far side of the galaxy, are even more poorly known. Each model makes different predictions about the total mass of gas in the galaxy and the rate at which stars are forming in the hidden regions. Getting a clearer picture requires radio telescopes with higher sensitivity and better angular resolution. The square-kilometer array, once fully operational, will be able to map the HI emission from the far side of the Milky Way in unprecedented detail. It will see through the dust and reveal the true shape of the spiral arms, the clumps of molecular clouds, and the bridges of gas that connect them. That map will not just be a pretty picture. It will improve our understanding of how the Milky Way's structure drives its star formation, how gas flows into and out of the disk, and how the galaxy has evolved over billions of years. The hidden arms are not just lost landmarks, they are active, dynamic regions where stars are being born right now out of sight, behind the same veil that keeps so many other cosmic secrets locked away. Every new wisp of radio light we detect from those hidden depths brings us one step closer to seeing our own home galaxy in its full, glorious shape. Beyond the Milky Way's hidden arms, an even greater structure dominates the nearby universe. The Shapley supercluster stands as the largest known concentration of galaxies within 650 million light-years of us. It contains more than 8,000 individual galaxies and has a total mass of perhaps 10 quadrillion times the mass of our Sun. This supercluster sits in the direction of the constellation Centaurus, but its full extent is difficult to measure because its outer edges reach toward the Zone of Galactic Obscuration. Astronomers have long suspected that a massive filament of galaxies and dark matter connects the Shapley supercluster to the Great Attractor region, which lies much closer to us at about 200 million light-years away. Such a filament would bridge two of the most massive structures in the local universe, creating a superhighway of matter that funnels galaxies and gas between them. If this connection exists, it would explain some of the puzzling bulk flows that we observe in the motion of galaxy clusters, because the gravitational pull of Shapley would extend all the way through the hidden zone, tugging on everything in its path. The challenge is to prove that the filament is real. Traditional optical surveys cannot see through the thick dust of the galactic plane, so the filament would appear as a gap in our maps. But two techniques offer a way forward. The first is weak gravitational lensing, where the shapes of background galaxies are subtly distorted by the gravity of the foreground matter along the filament. By measuring these tiny distortions across a wide field, astronomers can reconstruct the mass distribution even where no light is visible. The second approach uses redshift surveys that operate in the infrared or radio, which can detect galaxies on the far side of the obscuration. Telescopes like the European Space Agency's Euclid mission and the Nancy Grace Roman Space Telescope are designed to conduct wide-field surveys in the near-infrared, exactly the wavelengths that can peer through the dust. They will map the positions and distances of thousands of galaxies behind the galactic plane, searching for the telltale overdensity that marks the filament. If they find it, the connection between the Shapley supercluster and the Great Attractor will be confirmed, revealing a structure that spans 500 million light-years and shapes the motion of our entire local universe. Until then, the filament remains a hypothesis, an invisible thread that may or may not weave through the hidden region, waiting for a telescope that can see through the curtain of stars and dust that has kept it secret for so long. A new generation of telescopes will soon pull back the curtain. After decades of peering through a stubborn veil of dust and stars, astronomers are on the verge of a breakthrough that could finally reveal what lies hidden behind our galaxy. The Vera C. Rubin Observatory, perched high in the Chilean Andes, is set to begin its 10-year legacy survey of space and time in the next few years. Its massive camera, the largest ever built, will capture the entire southern sky every few nights in optical light. But Rubin's real power for the zone of obscuration lies not in seeing through the dust directly, but in detecting the faint gravitational distortions that betray the presence of hidden mass. By measuring the shapes of billions of distant galaxies, Rubin will map the dark matter that weaves through the obscured region, revealing the filaments and clusters that have been invisible for so long. Meanwhile, the Nancy Grace Roman Space Telescope, set to launch later this decade, will observe the sky in infrared light, the very wavelength that can cut through the densest patches of interstellar dust. Roman's wide field of view will allow it to survey the galactic plane far more deeply than any previous space telescope, spotting galaxies that have been completely hidden from optical view. It will also search for the faint glow of the warm, hot intergalactic medium, the missing baryons that may be hiding behind the Milky Way, and it will measure the distances to thousands of galaxies in the zone, filling in the missing pieces of the cosmic web. And then there is the Sgr A, a radio telescope so sensitive that it will detect the faint whisper of neutral hydrogen from galaxies billions of light-years away, even through the thickest clouds of dust. When the Sgr A begins full operations in the late 2020s, it will map the gas content of the entire hidden region, revealing the high-velocity clouds, the Magellanic Stream's obscured segment, and perhaps even the elusive dark galaxies that have been hypothesized for so long. Together, these observatories will turn the zone of galactic obscuration from a blank spot into a frontier. They will answer the question of whether the Great Attractor is just the tip of an even larger structure, whether the missing baryons are hiding in plain sight, and whether the cosmic flows that sweep our local group through space are driven by hidden attractors or unseen voids. The mysteries of the zone have endured for as long as we have mapped the sky, but with each new telescope, the veil grows thinner. The secrets behind our galaxy, the ones that have waited billions of years to be seen, are finally about to come into focus. And when they do, they will not just fill in a map, they will rewrite the story of our place in the universe.